So before we discuss the superscalar processes, we have to understand a couple of more concepts. And the first one is what is called as register renaming. So we'll discuss what is register renaming and what is the need for register renaming. So I've used the concepts from this chapter 5 of Shannon Lipasti for register renaming. You can also refer to this course which is available on YouTube, part 2 of the HPCA course from Georgia Tech for register renaming. So the topics we'll try to cover here, firstly in this and the next video are what is called write after write dependencies, the difference between true and false dependencies, how do we resolve this with register renaming, and the concept of a register allocation table. Once we cover this, we're going to discuss the next concept, which is multi-cycle execution, the need for what is called a reorder buffer. We've already done static scheduling and we'll now do uh, dynamic scheduling or what is called as superscalar processes. So let us recall that the original 5 stage RISC pipeline has these stages, which is the fetch, decode, execute, memory access, and write back. So when we say write back, it is writing back to the architectural registers. So if we have registers from R0 to R31, so these are the architectural registers which are available from the ISA. So when we say write back, we always say refer to the architectural registers available in the processor. So now when we move to the out of order or superscalar pipeline, we're going to discuss this in more detail next, but in order to understand superscalar processes, we need to understand the pipeline and also a couple of concepts. So basically here we move to a 7 stage pipeline. So the fetch and decode remain as it is. We're going to introduce a stage called dispatch or rename, where we're going to do the renaming of the registers. So once we do the register renaming, we're going to issue the instructions to the execution unit. Then the execution is going to happen. This is going to happen out of order. We're going to discuss that later. The memory access step is also part of this execute step. And then the instruction is going to complete its execution. And we're going to write the results not to the registers, but to a buffer. So let us right now understand that it is just writing it to a buffer. The need of this buffer and why do we have this stage at this point and all that will be explained once we start the superscalar processes. So the difference I'm trying to point out here is that we're not writing it back to the architectural register at this point. We're just writing it to a buffer. And then finally, there is the 7th stage, which is also called uh, the commit stage. This is also sometimes called the retire stage in some books. And this is a stage wherein we're going to write the registers back to the architectural register file. So we have written it to the buffer. Let us now call it a buffer. And then finally, we're going to write it to a architectural register. So this stage is the 5th stage in our previous step. So this is the architectural register write back. Whereas in the 7th stage pipeline, we call that a commit step, where we're going to write the register value back to the architectural register. So let us now understand that there are these steps currently so that we can go ahead with the register renaming concept. Okay, so now let us come back to what a compiler does. A compiler generates code. It takes the high level language code, let us say C code, and converts it into assembly, which is specific to the ISA. So generally it uses 2 steps. The first one is it generates assembly code. It assumes that there are infinite number of registers available. And then finally in the second step, it maps these registers to the architectural registers available with the ISA. So if you have R1 up to R32 or X0 to X31, it is going to map these registers, which it initially assumed as infinite, into these architectural registers, which is specific to the ISA. So these are the 2 steps followed by the compiler. Okay, so with this background, let us now look at what is called as a write after write dependency or a hazard. And then how do we resolve this with the help of register renaming? So now the compiler has produced this code, and then let us assume that the processor has multiple functional units. So which means that if you look at IF, ID, and then it has multiple functional units. So it has EX for, let's say, for example, addition, it has another EX stage for addition, then it has another EX stage, for example, for multiplication and so on. And let us, for example, assume that each of them takes the same number of cycles. So let us assume for now that each of them takes just one cycle to execute. So we have a processor which has multiple functional units, and each of them can execute, and therefore at any point in time you can execute multiple instructions in the same clock cycle. And of course they have to be independent. So if there are dependent instructions, you will have to resolve them before you execute them in the same cycle. So let us assume this sequence of instructions, and let us assume, for example, the IFID has already happened and we are just in some current cycle, and we are currently doing execute for this particular instruction. So since there is a dependency for these two instructions on R1, you cannot do EX in the same stage. Otherwise, you could have sent this second instruction to this particular, the second EX unit. So the first EX unit has got the first add, and you could send the second add to the second EX unit because there are two EX units available in the same cycle. But then because we have a dependency here on R1, you cannot really execute the same in the same cycle, and therefore you have to wait till the previous instruction completes its execution so that you can forward that value of R1. Okay, so let us assume that for now. Now, what about the third instruction? The third instruction is not dependent. It has R3 and R2 available, so it can start its execution because we have parallel execution units. And also similarly, the next instruction has R10 and R9 as the sources, and therefore that also does not have any dependencies. So here we are assuming that this third instruction, third EX unit can also perform addition. So you can send in that add instruction also to the execution unit. So currently that is our assumption. So now let us see what happens here. So now there is an R4 here and there's also an R4 here. And let us say after a few cycles, you are trying to read the value of R4. So now because we have delayed this particular instruction due to this R1 dependency, the write back of R4 is going to happen at this particular clock cycle 7. Whereas the write back for this particular R4 has already happened in cycle 6. So now which is the value of R4 that the sub instruction actually needs? The sub instruction actually intends to read the R4 from this instruction because that is the latest instruction and that is how the compiler has generated the code. But then what ends up happening is that the write back of R4 has happened in clock cycle 7 for this add instruction, and therefore this sub instruction will end up reading this value of R4, and that is actually the wrong value of R4 for sub. So this is what is called as a write after write, because you're trying to write to the same R4 after another instruction has written to the same R4. So that is why it is called a write after write dependency. And in this case, you should also note that reordering of the code also becomes difficult. For example, if you try to reorder this add instruction before this, then it will become kind of difficult because even in that case, you're going to read the wrong R4. So that is why this write after write dependency, which happens in certain types of processors, which have this kind of multiple functional units and then which have multiple cycles of execution. So for example, um, you could have another execution unit mul, which is going to take 5 clock cycles to execute. So EX1, EX2, EX3, etc. till EX5 and so on. So in such types of processes, write after write dependencies do occur and therefore we need to resolve them. Now, what is the reason for a write after write dependency? The issue is that the R4 register was reused. So this is an example of what is called as, the technical term is called register reuse. So this is an example of register reuse here. The compiler could have generated a code such that you do not have this R4 reused here. You could have just put in R15 or some other register. In that case, this kind of a dependency would not have occurred. So therefore, the reason for this write after write dependency is that the register has been reused, and importantly, the register has been reused at the destination. So the R4 here in this add instruction and the R4 here in this add instruction have been reused at the destination, and that is why it is called as a register reuse at the destination. And why did the compiler do this? Because it thought that there were a limited number of architectural registers available, and probably there is more code which needs other registers, and therefore it has reused the registers. So one of the resolution for this, or the important ways in which we resolve this, is to rename the destination registers, and that is how we resolve this. And this is called as register renaming. So there is another way of trying to resolve this write after write dependency. So for example, what you could also do is, if you have the same register at the destination, you could wait, you could stall, and do the write back after the previous one has written back. So what this also means is that you do what is called as an in order write back. So in the previous case, if we look at this, we were doing what is called as an out of order write back. So basically this is instruction 1, 2, 3, and 4. You're writing back instruction 4 before instruction 2 writes back. So this is also called as out of order write back. So instead of doing this out of order write back, you could also do what is called an in order write back. So you write back instruction 4 only after instruction 2 has written back. So basically we preserve the order during write back. So that is another way of doing it. But then in that case, you actually stall and then waste the clock cycle. So register renaming is a better way of doing it. So now the question is R4 a true dependency? So now if you look at R1 is a true dependency because you definitely need this value of R1 in order to start this instruction's execution, because otherwise you cannot really read this R1. Now is R4 a true dependency? So now here comes the two definitions. What is called as a read after write hazard. So now this is what is called as the read after write, which you're already aware of. Read after write hazard. This is what is called a true dependency because this has to be resolved, and without that there is no other workaround. So this has to be obeyed. True dependencies have to be obeyed. Whereas write after read and write after write are what are called as false dependencies. You can also call it name dependency, or it's also called anti-dependency. Why it's called name dependency, as you might have already guessed, it is because it depends on a certain register. In our case, R4 has been reused. If you were to use R8 instead of R4, the name would be different and therefore there would be no dependency. So this write after write is called as a false dependency. So now if we rename the registers, how would we do it? We would rename this R8, and therefore the R8, the R4 here earlier would also be renamed to R8 because you actually need this register. And now in this case, there is no real hazard here because you can still go ahead and write back R4 here and write R8 here, and this sub will still read the correct value of the register. So therefore, even if you were to do what is called the out of order write back, that is you write back instruction 2 before you write back instruction 4, you will still have the correct results for the sub instruction. So this is an example of how you do how you do register renaming to resolve the register reuse issue.